Hi everyone, so to finish off our topic today we're going to be looking at nuclear fusion. So the outcomes that we have related to fusion are being able to calculate the energy released per fusion reaction. We also need to compare that amount of energy to a standard chemical reaction and also relate this to the sun and explain some advantages and disadvantages of nuclear fusion over nuclear fission as a future power source. So firstly, what is nuclear fusion? So we've talked about fission, where a single nuclei actually undergoes fission and it breaks apart. Nuclear fusion is actually the combining of two nuclei to form a single nucleus. So for example, what we've got here is a deuterium, or a heavy hydrogen is getting combined. So two of them are getting combined to actually form a helium atom. So we had two hydrogens, now we have helium. So this is a fusion reaction. Now one of the byproducts, or a couple of the byproducts that we have as we have a look at this reaction is we've got a deuterium plus another deuterium over here, and we have the helium-3. The other thing that we have to take into account here is we're also releasing a neutron and 3.3 mega electron volts of energy. So it's a really massive energy production in this reaction. So this one's called a DD reaction because you've got deuterium with deuterium. The other thing that might happen is you've got another isotope of hydrogen, which is a tritium, which has 3 nucleons. So we've got a deuterium, which is a hydrogen with a hydrogen with 2 nucleons, and a tritium is a hydrogen with 3 nucleons. So in this reaction, which is a DT reaction, we've got a hydrogen getting added, or a deuterium hydrogen getting added to a tritium hydrogen, and it's producing a different version of a helium. So it's a helium-4 isotope. In this reaction, we're also getting the neutron being produced, so we have helium plus the neutron, just like we did before, but this time we're getting 17.6 mega electron volts of energy just from one fusion reaction. So what you can see here is that there's a huge amount of energy being produced, and the reason for this is that the total mass of the reactants is actually much greater than the products. So if we added up all of those parts, and also the products, then the missing energy, our mass defect, is actually released as energy, and we can calculate that using our E is equal to delta MC squared. So if nuclear fusion produces so much energy, well, why aren't we doing it? Well, there's a couple of reasons, but the main ones to note is that the biggest difficulty in causing these reactions is actually the repulsive forces between the positive charges in each of the nuclei. So because the nuclear forces are such short range, the two nuclei have to be brought together within 1 nucleon diameter for this reaction to actually take place. So this means that the electrostatic repulsive force of the protons needs to be overcome, which is a really difficult thing to do. So looking at an example here, if we have to calculate the amount of energy that's emitted during a fusion reaction, here we've got 2 hydrogen isotopes. We've got 2 deuterium nuclei coming together, and they are forming a tritium isotope, and also a neutron is being released. So if we have a look at the mass of the reactants and then we calculate the mass of the products, we can figure out that there's a mass defect of 5 times 10 to the negative 29 kilograms. So using our E is equal to delta MC squared equation, we can work out that that equation particularly releases 2.8 mega electron volts. All right, our easiest place to find a fusion reactor is actually in our sun. So the source of energy from the sun is produced by nuclear fusion of hydrogen turning into helium. So there's a few different reactions that happen in the sun. There's standard hydrogen, 2 standard hydrogens coming together to form our standard a deuterium. There's also a hydrogen coming together with a deuterium to form a helium 3 isotope, and then there's also 2 heliums that can be broken down to produce 1 helium and 2 hydrogens. So there's a few different ways that these reactions are occurring on the Sun. So H4, or He4, is produced, that's the stable isotope of helium, as well as 2 protons which can initiate the reaction series. So these 2 protons that are produced here, they can actually continue to undergo fusion and potentially go back to this and continue the cycle. Now the Sun's core is about 20 million degrees, so that's high enough to actually excite the atoms to release gamma ray photons and also other radiation of low frequencies as they revert back to their lower states. And it's also high enough to start the proton-proton reaction. So what we need for this fusion reaction to occur and to overcome those Coulombic repulsion forces is intensely high pressure and ridiculously high temperatures. Alright, so there's a few really good advantages of nuclear fusion. Number one, that hydrogen is actually the most abundant element in the universe, and the fuel supply is therefore no problem in the future. So in the case of fission, we actually have an estimated uranium supply for about 200 more years. So fusion is actually a cleaner process than fission, so therefore there's less radioactive byproducts. There's none of those nasties that actually require handling like you do in a fission reaction. Safety precautions with the reactor can be less stringent than a nuclear reactor, as the danger of actually venting that radioactive material into the environment is far less than it would be with a fission reactor. It should eventually cost far less to produce electricity because the fuel is more abundant and therefore much cheaper. And also, a huge advantage is that the energy output from a fusion reaction is far greater per nucleon than that of a fission reaction. However, there are a few disadvantages of fusion, the main one being that our current technology just is inadequate to produce this reaction. So basically what we're using currently are toroidal donuts, which use a magnetic field to actually contain the reaction. But unfortunately, as I said, our technology is not as yet advanced enough to be able to sustain anything of note. It's very expensive in terms of research and development at this stage, being that we just don't have the available technology, so it's quite expensive to research and try and come up with a way to handle this reaction. And then the production of high temperatures and the containment of high kinetic energy nuclei is a problem, again, just because we just don't have that technology. But hopefully in the future we'll be able to sustain these really high temperatures and pressures in an Earth environment so that we can make this happen and actually produce far more energy instead of messy energy like coal and nuclear fission.